All right, Math 201 students, this is the pre-video for sections 3.4, 3.5, and 3.7. Just going to do a few examples from each section to get us started. So looking at 3.4 and 3.5 are actually the same topic, but optimization problems usually go into a more algebraic or geometric discussion when you take like a traditional Cal 1 class. So we're going to be focusing more on the business applications of this and the economics applications. So what an optimization problem is it's when you're solving for a maximum or minimum of something. So you're trying to either maximize profit or minimize your cost. So our guidelines are that you need to identify all the given quantities and all quantities to be determined. If possible, if it's something geometric or something you can draw, make a sketch. You'll write your primary equation for the quantity that is to be maximized or minimized. So if you're maximizing profit, you have to have the profit function. You will reduce this primary equation to having a single independent variable. So you may have to resolve something, plug some things in depending on how difficult the problem is, and determine the feasible domain of your primary equation. Obviously, you know, like if we're solving for time for something, you wouldn't want to have negative time. So just make sure that your domain is feasible. And then you determine the desired maximum or minimum using calculus, which means taking derivatives. So we're going to look at this first two examples here in section 3.5. It says, in business and economics, we often want to maximize profit and revenue, and we want to minimize our cost so that our business can be a functioning one that will last for years. So we can use the guidelines from the previous sections to find maximum and minimum values. So this first one is already kind of set up for us. It says, find the number of units that must be produced to maximize the revenue function. So that tells us what function we have to be able to do this problem. Excuse me. And then it says revenue function is, immediately they give it to us, r equals negative x to the third plus 150x squared plus 9,375x, where r stands for the total revenue in dollars and x is the number of units produced and sold. Also, they want us to find the maximum revenue. They actually want us to figure out what that maximum amount of money they're going to take would be. So we're going to take the derivative of our revenue function, which would then be negative 3x squared plus 2 times 150 would be 300x, and then plus 9,375. I would pull out a negative 3. I think they're all divisible by 3, so that makes this x squared minus 100x and minus 3,125. Now, obviously, you would have to come over and think of the factors of 3,125 that work, but because this is a video, I'm not going to list all my factors out. So I found out that it was negative 125 and positive 25. They multiply to negative 3,125, but they add to negative 100. So I'll write those both down, and that was just looking at factors. I was just checking all the factors of 3,125. So if we solve each of those, then we get the possibility of 125 units, and the other possibility is negative 25 units. Now, obviously, you're not going to produce negative units, so that's not feasible domain. So we need 125 units sold slash produced, since they use both words, to reach a maximum revenue, and we want to find out what that is. So now I want to double check and make sure that this, since there was only one answer, I knew that it was going to have to be the maximum, but let's say that had been positive 25 too. How would you know which one was the max and which one was the min? Because I kind of jumped over that step since there was only one possibility. You would put 125 in the middle of your number line, and then you would pick a number smaller, so say 10, something bigger, say 200, and you would plug them into r prime. So r prime, if we plug that in, that would be a negative times a negative, because I'm plugging it into my factored form, and then times a positive. So that's a plus overall for that region. And then if you plug in 200, you'd have a negative because of the negative 3 times a positive, which is a negative. And that's increasing to decreasing, so that is a maximum. So you can always verify that if you want to. But if you have a single possibility, it's pretty much the answer. So to figure out your revenue, because we want to know what that would be, we need to plug 125 back into the original function. So r equals negative 125 cubed plus 150 times 125 squared plus 9,375 times 125. I already worked through that, and that gives us a max revenue in dollars of 1,562,000. That's not a good six. 562,000 and $500. So that is the max revenue. So this is the number of units. This is the max revenue. All right, the only other one we're going to do from this section before we move on to 3.7 is the second one here. And it's worded just slightly different, but similar problem. So this one says, the company has determined that the total revenue in dollars for a product can be modeled by the function r equals 48x squared minus 0.02x to the third, where x is the number of units produced and sold. What production level will yield a maximum revenue? Production level means units. So how many units would that be? So again, we're maximizing revenue. That's important. So that means we do have the correct equation. So this would be r prime equals 96x minus 0.06x squared. We would factor out an x. That would leave me with 96 minus 0.06x. You could try to pull out a GCF for the number. I didn't think that was easy, so I just left it in there. And then I would solve this, which ended up giving me 1,600 units. 0 units doesn't make sense. You're not going to maximize your revenue if you're not making any money. So again, I could show you, I could actually put 0 on here and show you that it's definitely not a maximum, just so you can verify that for yourself. But we wouldn't make negative units. That doesn't make sense. But what if we made 10 units? But we can still check. So negative 10, positive 10, and let's say 2,000. If we plug those into our r prime, if you plug in the negative, that would be a negative times a positive, so that's a negative. If you plug in 10, that would be a positive and a positive, so that's a positive. And 2,000 would be a positive times a negative if I work it out, which is a negative. So notice this is a minimum, but this one is a maximum. So I can always verify it really is a maximum. So we would get production levels, and you don't need the actual revenue in this one because it only asked you what was the production level that gives you that max revenue. It didn't ask you to find the actual revenue. So the production level for max rev is 1,600 units. So we'll be doing some more of these in class. We're going to look at some minimizing cost and some other types, but that's just a taste of those. So let's jump all the way down to the section 3.7. We're only going to do one of these since they are slightly longer than an average problem. This is summarizing everything that we've taught you so far in chapter 3. It's called the curve sketching summary. So essentially, we're going to put together everything we know about these functions, about whether or not they are increasing on regions or decreasing, if they have maximums or minimums, if they have concavity, up, concave, down, do they have points of inflection? So everything we know, plus some things back from chapter 1, like what are the x and y intercepts? What is the domain and range? All of that gets put together so that we can sketch the most accurate graph we know how, now that we know algebra plus calculus. So sometimes these are not so easy to find the x-intercepts, and this one I can at least use quadratic formula to do. So you'll see on the directions for like the review and the test, it might say something like the x-intercepts are not the emphasis, but since I can do the x-intercepts on this problem, I am going to work through them. To find your x-intercepts and y-intercepts, remember you plug in 0 for the different variables and solve that. So let's do, if I want to do my x-intercepts, I plug in 0 for y. So this is my work for x-intercepts. So that's 2x squared minus 4x plus 1. You could try factor by grouping, but it does not work. This does not factor. So the only way to get those is to do the quadratic formula. So remember, this is a, b, and c. So negative b would be 4 plus or minus the square root of regular b squared minus 4ac all over 2a. So that is a formula from algebra. And this would be 4 plus or minus the square root of 16 minus 8 all over 4. I can keep working this out. That's going to be square root of 8. Square root of 8 reduces. That would be a 2 on the square root of 2. And then I can reduce this down into a 1 plus or minus a square root of 2 over 2, because 4 divided by 4 is 1. 2 square root of 2 divided by 4 is just a square root of 2 over 2. So that's 2 separate x-intercepts. We want to write both of them as ordered pairs up here. And then once we do that, we will look at how to get the y-intercept. So let me type these in. Sorry, my pen was malfunctioning. There we go. So this is 1 minus the square root of 2 over 2, comma 0, because it's an x-intercept. and 1 plus the square root of 2 over 2 comma 0. Now this is the answer I like for exactness, but if you're going to graph this, you're going to round it. So I would turn these into decimals is by just using your calculator. This one comes out to about 0.29 and this one's about 1.71. So now to get my y-intercept, I need to plug in 0 for all the x's. So 2 times 0 squared minus 4 times 0 plus 1, just plugging it in for all the x's, and this is just a 1. So my y-intercept is at 0, 1. Now the next line down asks us for relative maximums and minimums, which means we need to know about the first derivative. So f prime of x is the derivative of this function right here, so that would be 4x minus 4. We would set that equal to 0, pull out the 4. So x equals 1. That's my only critical value. I'm going to kind of bar off the x-intercepts from this. So my critical value goes in the middle of my number line. This is negative infinity to 1, 1 to infinity. Plug in a number less than it and a number greater than it into my first derivative. If I plug in 0, I get a negative 4. If I plug in 2, I get a positive 4. So this is a decreasing region, and this is an increasing region, and this means that this would be a relative min. So I have a relative min at 1, comma, I don't know the x value yet. So I have to, or the y value, sorry. So I have to plug it into the original function. So f of 1 is going to be 2 times 1 squared minus 4 times 1 plus 1. Always go back to the original function when looking for your ordered pairs, because that is where the ordered pairs come from. So this is at negative 1. So 1 comma negative 1. We do not have a relative maximum because it would have shown up throughout the process, so that would be none. We also know about increasing, decreasing. They didn't ask us for it, but sometimes I'll write it down. We're increasing 1 to infinity and decreasing negative infinity to 1. Sometimes it's just nice having that all in one location. All right, and then I want to do my concavity and points of inflection, and then I will talk about how this has no asymptote. I'm going to go ahead and say that because it's a polynomial. You only get asymptotes if you have a rational function, or something else that possibly has asymptotes like exponentials or logarithms, which we have not discussed yet. So we need to take our second derivative, which means we take the derivative of the first derivative. I'm going to do this one in red. So f double prime of x would just be 4. And that is always greater than 0. So that means we are concave up everywhere, from negative infinity to infinity. Now, if you got like a negative 4 here, we would say that's always less than 0, so that'd be concave down. If you had an x, you would solve for a value, like set it equal to 0, find, and do a table again. But if you ever get a second derivative that's just a number, it only matters if it's positive or negative, because your whole graph will either be all concave up or all concave down. Now, so let's write that. That means there's no point of inflection because there was no x in f double prime. Okay, so let's go up and fill out our chart. This is points of inflection, not existing, but concave up on whole number line. Okay, and this graph is a parabola. I mean, I already knew that going in because it's an x squared. So we're going to sketch what we know, and that's going to help us see the whole picture and a lot more detail than we ever were able to give before when we did this in algebra. Now for parabola, this isn't very interesting to most students because you're like, I already know how to graph a parabola. But for harder functions, this process will actually give us really good sketches with the least amount of work, in my opinion, instead of just random plug and chug. So I need to have my points that I know are my intercepts. So hang on, this is 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. I had an x-intercept at about 0.29 without going back up there, so that's right about here. And then I had another x-intercept at about 1.71, which is probably right about here. Then I had 1, negative 1 was my relative minimum. This is the lowest the graph can ever get. And then we had 0, 1 was our y-intercept. So notice you can see the parabola shape here, but this also makes sense because from negative infinity to positive 1, the graph was decreasing and concave up. From 1 to infinity, the graph was still concave up, but it was increasing. So that is how we got a very detailed sketch of this parabola using what we know about intercepts and then using calculus to help us with the maximums, minimums, and points of inflection. Hopefully you guys found this video helpful. It is just a teaser to what we're going to be doing in class. We'll obviously look at some more interesting functions there. And that's the end of this video.